So this is the second module. As I told you, this is all to do with the multipath fading. This is actually the first part of the multipath or the channel for that matter. Okay. The type of channel also, I guess most of you are familiar now because you have done or at least are doing the ITC. There also you will find that there are lossless channels, noisy channels, eraser channels, all those channels you are discussed with. But in this case, we will not discuss on that aspect. We will take it into account the physical constraint that a channel might have and the properties that it possesses. So based on that, the first thing that is very important in this light, that this is what we call as the multi-path scenario, which I guess most of you are familiar with. That whenever we have a base station which is transmitting a signal for that matter, and it should be received at a particular location, maybe a person who is inside this car and who is having a phone. But ideally, the condition is that it should be a line of sight or a direct path that will lead from the base station towards the user. But practically that never happens, as there are multiple reflectors or attenuators or scatterers that will provide multiple copies of the same signal at a different point of time to the same user. So that is the effect of multipath fading on a wireless signal. Okay, that is what the idea is. Now what we have to do is, when we are looking at our scenarios, that when we are talking on the phone or we are calling someone or whatever it is, we don't experience any problem whatsoever because we get a clarity in sounds and everything. And that happens because we are taking into account whatever the multipath process the signal might go through, and we build the transmitter as well as the receiver based on that. So that is primarily the reason why we are getting a much better throughput at the end. So that is where the research is actually going on, where people usually invest lots of energy in making these channel models and to make this signal transmission and reception to be faultless. That is what the idea is. Now, based on this, we also come across three basic phenomena, that what are the losses that might happen. So the first thing is the propagation loss, which basically the natural expansion of radio wave when it's free space. As we all know, that with distance, when you have an omnidirectional antenna and you are moving from the base station towards the farthest corner, we have observed that the energy will go down, as well as we have observed in case of our LT experiment last day for some of you, that at least when we are moving from one point to another with distance, the throughput also varies. Okay, even with the velocity, we have observed that the throughput tend to come down. So that is what the observation is, that we have some kind of a propagation loss we need to take into account. If we want to eliminate this propagation loss, that we assume that there is no propagation loss, then that's a hypothetical scenario. That is not a cellular design. Okay? So, but actually by this time we were assuming that the cellular concept, whatever we did, we haven't considered channel up till this point. So now this is the point where we are including these losses in the signal, and we are going to find out what is the received power. So that is primarily the observation. Now we have absorption loss. Absorption loss or penetration loss is because of the different medium through which it is passing. Okay. Even this will be accounted with something called as partition loss. At some point of time, I told you as an example that suppose you are making a measurement at TT135, your indoor model or indoor loss will be different to that of what you are measuring in TT620. It's because of the attenuators being different. We don't have any computers over here in this lab, but those systems will have a portion of losses that you need to include while making the linker. So that to give an account of this is one of the observation, that for a frequency range of this much, okay, we can have this many dB losses for elements or materials which are very commonly used. You see the plywoods here, okay, so these are very commonly used materials. So they will have an amount of absorption loss. So each one of them will have a certain amount of loss. Now you multiply the number of times it has been used. So naturally there is a huge loss that is you have to take into account. So if based on this, the transmitted power should be calculated. So transmitted power minus the overall loss, that will be your received power. So based on that, we define three definitions. This is already pretty much known to you from the concept of physics. But ideally, with respect to RF communication, we have different definitions for reflection, diffraction, and scattering. So please note down this as a definition, because this usually comes as a short note of 2 marks. So when we are looking at when we are looking at the reflection for that matter, okay, when we are looking at the reflection for that matter, we have the obstruction or foliage, okay, which has a dimension much greater than the wavelength of the signal. This is the only and the best definition that we have. This is given in Rappaport as well. So the reflection we will call a loss or a phenomenon, the basic propagation mechanism as a reflection, whenever we are looking at the obstruction of foliage which is having a greater dimension of that of the wavelength of the signal. By this what we mean is, we actually can have, you can take an example, as I told you, the surface of the earth or the building or the wall, whatever we call it, they will always have a dimension which is greater than the signal, okay, with the wavelength of the signal. So ideally, suppose you are moving from gate number 3 towards TT. So when you are experiencing towards TT, the food court and the TT building or the TT annex building, the walls of them will provide a reflection to the signal. Just to imagine in that way. So the signal, when the multipath signal will go through reflection because of the walls. Now, if you consider only the TT building, okay, just if you imagine, if you go towards TT, I don't know whether you have experienced or have you come across to that, you will find that in TT, we will have some kind of a sharp edges at the corner or the sides of the building. Have you seen that in TT? So if you have that sharp edges will give you a diffraction. Okay. So you can see when the radio path travels with transmitter and receiver is obstructed by a surface with a sharp irregularities. So in terms of RF communication, we now define the diffraction in a different way. That when you are experiencing irregularities or the edges, especially the knife edge, we will have a geometry called as knife edge geometry, through which we will find out that loss, how much is happening with respect to a diffraction. So this part of irregularities will include some kind of a diffraction loss to the overall system, along with the reflection, whatever is happening because of the walls or the dimensions of the object. So that is one of the observations. These two are very important actually, because we will see that for reflection we have a different set of models. Okay, we will call that as two-ray ground reflection model. We will study that. Okay, so we will try to model this particular phenomena, and also for diffraction we have something called as knife edge geometry. That also will give you an understanding on what the amount of diffraction loss that may have. So we will check that later. And the third phenomenon, which is again very common, and that is called as scattering, where the medium has objects which are smaller or comparable wavelength to that of the smaller size to that of the wavelength of the signal. So reflection and scattering is basically the opposite way around. In reflection, the wavelength of the signal is less than the size of the object, and in case of scattering, the size of the object is much smaller compared to the wavelength of the signal. And as you can observe here, the raindrops, okay, the snow on the rough surface, the granules, they will have also a role to play. So you are having a scenario, you can observe that you don't experience it, but it's actually happening. That while you are traveling from, as I told you, TT to, or maybe ground, the gate number 3 to TT, all the buildings will have the walls, and those will constitute some kind of a reflection loss to your overall received signal. Then you have your specific buildings which might have corners or edges that will specifically add some diffraction loss. Then also you have the granules or the dust or the particles which might constitute the scattering loss. All this loss put together should be subtracted from the transmitted power. It will reduce the transmitted power, hence the received power will not be sufficient enough. Now, as we all know that there needs to be a sufficient received power at the end or at the receiver so that a voice communication can take place. So based on that, you have to modify the transmitted power and you have to take these losses into account. So these losses needs to be modeled. That's the idea. That's why you will find that for many of you, when you did the experiment on LT last day, when you are dropping down the path loss and shadowing model, there are multiple models coming in, right? Free space path loss, log distance, log normal, like that, multiple options were coming. All those models are defined to find a quantitative measurement of the loss. Okay, so they are all assumed, they are all empirical or analytical models that will give you an understanding on the loss that is happening. If we get hold of that loss, we will subtract that from transmitter, and then that will be the resultant received power. Okay, so that is what we are going to do overall throughout this. So based on this, the first thing that we will skip this. We already know this actually, that with distance the received signal goes down. This is just an intuitive understanding. We'll come to this at some point later, that how we define the fading. Okay, we usually do it with two respects. One is called as the small scale fading, the other one is called as the large scale fading. Now with small scale fading, what we usually do is that if we take into account the rapid fluctuation of a signal. Suppose you want to measure a power. What is the power profile for a given distance, or rather suppose within a particular from one point to another, but you make a measurement at a very rapid pace, like you make it measurement like each 1 hour, okay, or maybe with 30 minutes. So when you are making those measurements, you will find that the profile will look something like this red graph, because it will go up or down based on the distance as well as the making when you are making the measurement. So the rapid fluctuation, if it is plotted, then we call that as a small scale fading. And when you are taking an average of it, okay, then we consider that to be a large scale fading environment. We'll see this small scale and large scale fading at some time later. We just introduce the term over here. You can see here the change is very rapid. Okay, so this is change is rapid and arbitrary. This is what the small scale is all about. And in case of large scale propagation, there is a local average based on which we try to measure. This is only that when we try to measure, we want to model a particular system, we need to take into account which one we choose, either small scale or large scale. We'll see that later. Sometime later it will be useful. The one that we are going to start today, and that is most important, and that is called as the free space propagation laws. I guess most of you are aware of this particular equation of received power, which is equal to Pt Gt Gr lambda square by 4 pi whole square d square L. I guess this is known to you. Many of you might have done SATCOM in that, maybe it has come. Because this is a generic free space propagation law. It doesn't exactly relate to wireless communication or mobile communication for that matter. So this is a first case, the free space propagation laws. Please note down this equation because this is very important. You have to follow this equation. There is no, I will give you a derivation of it after a certain 2 slides after this. But that is not exactly required for the time being. So you have this Pt Gt, which is nothing but the power transmitted as well as the gain of the antenna, and the received power is also receiver's gain is also Gr. And if you have a knowledge of this lambda, which is again given by C by F, because you know the frequency at which you are operating with, so C by F will give you lambda, and you have the D, which is basically the distance where you are making the measurement. So transmitter and receiver will have a separation of distance. So that D is this D. And loss is the overall loss factor, which usually comes to be 0 or 1, is usually considered to be 1. Okay, that's an environmental loss factor that usually considered. So L you can neglect, that usually is 1. Okay, so now this is what we call as the free space loss. That's because only you can see in the left hand side we are calculating with respect to the received power or PRD. So this is also a function of D. So that's why the distance is very important. Remember last day when we were doing the experiment, I told you that vary the distance. Because the way you are making the movement of the distance, this received power will also vary. It's a function of the distance. So that is what the main idea behind this equation. And also in light of that, please note down this as well. This is a generic formula for gain, calculation of gain of an antenna, which is given by 4 pi. A is the aperture of the antenna. So G is equal to 4 pi AE divided by lambda square. This comes from the antenna theory. Most of you have not done it. So that's why I thought of giving you over here. So this is the gain of the antenna. We'll see that. It will be helpful at some point of time. Please note down the equations, the 3. Lambda is equal to C by F is pretty much known to you. But the other two, please make a note. Now, by looking at this, now the question comes in, which is a very tricky one. Can you cite any disadvantage of this? That's the first the important question that we need to handle, because based on that we will follow. Because ideally from this the numericals are pretty easy. Most of the data will be given to you. You have to just drop in and you get the answer. Simple as that. Nothing more than that. In many of the cases GT/GR will be 1. So you don't have to calculate that as well. So it becomes very easy. But the first question is there any disadvantage or any loopholes in this particular equation or this particular model? We have the points, you have the equations. Can you just identify for me? Is there any problem with this? because this is very important to understand. Can you observe any difference? Any specific problem that you might have? Yes, that's one. Or to be specific, first point, what it gives you, free space propagation loss or model is applicable to LOS path between the transmitter and the receiver. This is the first of the case where they are including the LOS. Now, as I told you, line of sight propagation is a very hypothetical scenario. You don't really get a LOS condition. So, this model actually is valid only for a line of sight communication. So, that's why I told you that in satellite communication and all, there the line of sight might be very, very important, and that's why it's being used there itself. But as far as the wireless mobile communication is concerned, the abstractions are much, much more. And when you are practically modeling a system, this is actually very hypothetical that a base station and the mobile device, or rather each and every mobile devices will always be at line of sight. So it's a fictitious thing. So that LOS part is basically one of the limitations of free space. Can you cite another drawback of this thing? Just check it once. What can be one problem if that is fine, because that is not coming to the equation itself. From the equation itself, suppose PT, GP, GR, all these things are taken care of. That is naturally needed. You are modeling a system, you need those inputs. The major problem with this is D. If D is equal to 0, what will happen? It won't exist. This model doesn't exist. Why? When it is D0 means that suppose you are making a measurement when the transmitter and receiver separation is negligibly small. So if that happens and you want to apply the free space loss, that happens to be a problem. That is where we come with a conclusion that you need a specific reference distance, or we call that as Fraunhofer distance, after which you actually can apply a free space propagation loss model. So please note down, or at least remember, that the limitations of free space are first, that it is only restricted to line of sight communication, and the second, when D is equal to 0 or very small, it is not applicable. Okay? Or actually, when it is D equal to 0, it's not applicable at all. So, in order to do that, what we are going to propose is, we are going to have this. Actually, we'll come back to that slide once again. So, the free space model, we have a far field region. We define this as far field region. Again, please note down this word, far field region, because this is the region after which the the free space model can be applied. As you can observe here, it is that region of a transmitting antenna beyond which, or beyond the far distance df, which is related to the larger or the linear dimension of transmitter antenna. So this df is given by 2d square, capital D square, by lambda, where d is the largest physical dimension of the antenna. So suppose you are making a measurement with respect to a free space. So basically you have to take into account what is the maximum dimension of the antenna possible. Because that is up to me, how you are designing an antenna. So if I know capital D, if I know lambda, 2d square by lambda will give us df. So this df, you can see that last line, that only when we are beyond df, if the receiver has further moved away, then only the free space expression can be used. So this is very, very important. So we have to find out that what is the far field region, or the Fraunhofer distance we sometimes call this, and we will try to find out that what is the distance after which it can be used. So we need some kind of a reference distance d0, and we need the distance at which we are making measurement, which is d. So now the distance has a two part. One is the reference distance d0, the other one is the distance at which we are taking a measurement. We'll see that after this particular slide, how it is being used. Before going to that, let us finish off with this explanation of this particular equation. So you can see we divide this into two halves. One is known as a PT-GT. Please note down this PT-GT, that is power multiplied by the gain. This is called as the EIRP, or effective isotropic radiated power. Given over here. Effective isotropic radiated power. This is a technical term given to that power multiplied by gain. And this is maximum power of transmitter in the direction of the antenna. So this is a maximum throughput that you can provide. Okay? Because as I told you, when you are accounting the loss, whatever the loss is happening, you have to maneuver somewhere the transmitted power. So this EIRP is a very important factor in that case. Okay. So this is one of the observation out of it. Another observation is the path loss. How do we calculate the path loss? Basically, we take the ratio of PR by PT by PR. We take a 10 log of it, so it will be in dB. So if you consider this one, minus 10 log of GT/GR lambda square by 4 pi whole square d square, keeping in mind L equals to 1. Okay, so as you can observe that basically in case of the equation that we have, PRD, if you just rearrange a little bit, PR by PT, then you come to GT/GR lambda square by 4 pi whole square d square. So that is what we are getting. So if you get that and you take a log of it, so the minus is coming because of that log. Now just tell me one thing. Okay, some there. So if it is minus, what does this mean? Think? It's a loss, correct? It's loss. Minus is indicating actually the loss. Ideally, it is coming from the log term itself, but ideally, this is significance is that we are looking at a loss factor. So that is what the idea behind free space. And the last equation, as I told you, this is also very commonly used in many of the numericals. You will get it that GT and GR, if it is 1, if it is an unity gain antenna, then you are substituting GT/GR 1 over here. So you are left with minus 10 log of lambda square by 4 pi whole square t square. So this D is basically where you are making a measurement. But the general solution should include D naught, which is a reference distance, and then you have to take into account what is D, where you are making a measurement. So the general equation would look something like, this is the general equation. So your general equation will look something like this. PRD, which is the received power at a certain distance D, is given by received power PR at D naught multiplied by D naught by D. Now this D naught is that small distance after which we are making the measurement. Okay. And if you change it to dB scale, you are getting some results like this. So PR dBm, if you can convert that in milliwatt, so it's 10 log PR D naught plus this 2 comes in over here, so 20 log of D naught by D. Ideally, when you come by, after Cat 1, when we start, you will find that something called as log distance model and log normal shadowing model. In that also, you will find that the very similar equations we are going to use. So ideally, that is this is a basic starting of that modeling part. We will see that later. But this is basically the generic equation for the modified free space equation, considering D naught as one of the factors. Okay. And let me just go back once. Okay. So this is what the Fraunhofer distance. So DF is already been mentioned over here. So in practice, as you can see, reference distance is chosen as 1 meter for indoor and 100 meters or 1 kilometers for outdoor measurement. So you can see the measurement also varies. Where you are making a measurement, whether it's an indoor measurement or an outdoor environment, the measurement or the reference distance will vary. Okay. So that is the basic idea behind free space. So if I want to check, you can see here, this is also very important. You can see D naught is just greater than DF. It can be equal to DF, but just greater than DF. Then D is even greater than what we are looking at D naught. You understood what? DF is what we have to calculate using this formula. So that's a Fraunhofer distance. So we have to first measure what is your PRD at that particular point. So D naught, suppose D naught and DF are same. So you are making a measurement of using free space model at D naught. Then keeping that as a reference, you have to find out what is the power at D. So for that, this equation needs to be used. Understood? In that, this part is coming from the free space equation. The PT, GT, GR, lambda square by 4 pi. So that is what the idea is. So based on that, maybe we can have a small calculation on the far field distance. So just do it, this 2 minutes of drill. Find the far field distance for the antenna with maximum dimension of 1 meter and operating frequency of 900 and 1800 megahertz. So your dimension is 1 meter, yes, given. F is 900 megahertz and your dimension formula is also given. So just find out what will be the distance, far field distance in both the cases, because you will find that both the cases the frequencies are different. So that is also an observation that with changing in frequency, you have a different set of far field distance. So that is what the observation. So please do it. Just 2 minutes you will need. So this is already given to you. Find lambda using C by F. Okay. Then substitute over here and this will be the answer for you. D is anyway in 1 meter. So ideally your lambda should be converted in a way that it comes to a meter kind of thing, so that you can substitute and get the answer. For the first case, what will be DF? 6 point something, 6.06 or 6. So basically, if you substitute over here, your okay, let me just give you one idea for people who are not able to get it. So it is 900 into 10 to the power 6. So it will be coming around 0.33 meters. So you substitute over here, and 2d square is 2 into 1 square. So your DF will come around 6 meters. Okay. Now if you consider this DF and the second option as DF double prime or prime with respect to 1800 megahertz, your DF double prime should come around 12 meters. Same formula, same thing, only except that lambda will come around 0.17 meters. So this is for the second case, D. So you can observe that with changing in frequency of operation, we are having different set of values of DF. So when you are, suppose you are making a measurement with respect to free space modeling and you are using 900 megahertz. Why 900 megahertz is important? What is the significance of 900 megahertz? GSM band frequency, correct. So 900 megahertz if you are using, then basically after 6 meter only, your 6 meter becomes your reference. After that, wherever you are making a measurement, keeping that as a reference, you have to go for it. If you are using a free space model, that's the idea. So this is a very simple problem, and suppose you are making a measurement at 1800 megahertz, your DF will be around 12 meters. That's the idea. Any doubt up till this far regarding free space? Because these are the main idea. So let us do this as a problem, because this is a very common problem, because when we go along with this, you will soon find that you will be needing these conversions at some point. So if a transmitter produces 50 watt of power, okay, express the transmitted power in units of dBm and dB watt. I will give you the solution directly because it's very important at this juncture to know this. Please note down each and everything whatever is written over here. So what we are doing is PT is 50 watt, okay, and assuming the carrier frequency as 900 megahertz. So if you substitute on PT, so you are taking 10 log of PT in milliwatt, okay. So you are converting, because the question is to find it in dBm. So this dBm, dB watt is, that's what is important in this case. So it is given in watt. In order to convert that, what you have to do is you have to take that 10 log of 50 multiplied by 10 to the power 3. Okay, so that is what we are doing. We are dividing it by 1 milliwatt. So that is why it's coming up. So it's coming as 10 to the power 3. So this is your direct giving us dBm, 47 dBm. Everyone understood what I did. This 50 watt was there, so I convert that to milliwatt by giving this. So now we are looking at a scenario, so 50 into 10 to the power 3. So the expression with dB will be called as dBm. Now the question is, most of the questions will be asking you to find it in dB watt. Okay. Now to convert that, you don't need to calculate anything. Just remember this conversion. 1 milliwatt is equal to minus 30 dB watt, or P dBm in power dBm is equal to P dB watt plus 30. So suppose you have got the answer in dBm, subtract 30 out of it. So you will get it in dB watt. So dBm and dB watt, this particular expression, this is very, very important. You will need this during your numericals. Because always this will create a problem that how to convert that from dBm to dB watt. So either you find out in dB watt, you change it to dBm, or you find out on dBm and you subtract 30 out of it. You will get it in dB watt. Because most of the questions in this will ask you to find the received power in dB watt, like the one that is given over here. So based on that understanding, can you solve this equation or this problem for me? This is a specific problem given in Rappaport, and it's a fundamental problem to solving free space model. Please do it. If 50 watt is applied to a unity gain antenna with 900 megahertz of carrier frequency, find the received power in dBm at free space distance of 100 meters from the antenna. Okay. What is the received power at 10 kilometers? So ideally, if this is, and also you can see, assume the unity gain for receive antenna as well. So GTGR is again to be 1. Now the one thing to be noted down over here is that 100 meters when we are looking at, that is basically your reference distance. Just understand this, because here nothing has been mentioned with respect to the dimension of the antenna. Capital D is not given to you. So you cannot find the Fraunhofer distance. Since you cannot find it, this 100 meters is what will act as a reference distance D0. So taking 100 meters into account, first find out what is the received power. Then you have to make the measurement at 10 kilometers. So your D will be 10 kilometers. So basically your D0 is somehow given, if I write in terms, so your D0 is basically 100 meters, whereas your D is basically 10 kilometers. So given all the specification and GTGR to be 1, please solve it. Give me the answer. At least PR D0 you can find out quite easily. So just try to find out what we. Okay, one thing before we start, can anyone give me what will be the dB watt if I try to calculate this one? Like directly I want to find dB watt. Nothing much actually. You take 10 log of 50. So whatever you get it, this will be your, it's like 17 it should come dB watt. So now we are looking at dB watt. Now if this is dB watt, so you add 30 to it. Understood? So that becomes dBm. So you can see this is what you are getting. That's what I was telling. Like you can either use dB watt, you convert that in dB watt, add 30 to it, or you take dBm, you subtract 30 from it. Whatever you, but don't do it both. Yes. So now you go back to the solution. Just substitute the data, okay, and give me the answer. All very easy actually, because you have the formula PR. You will consider this to be D0 is given by 50 multiplied by 1 multiplied by 1. Your dimension, your lambda square, we have just calculated, right? Last problem, 900 megahertz we did. So this will be around, I think this one, by 4 pi whole square. L should be considered to be 1 as I told you. And the distance square, because this is why we are doing it, because PT, GT, GR, lambda square by 4 pi whole square, D0 square. This is the formula that we are referring to. So just substituting the data we get this. So this is equal to, because here we are taking 50 watt, okay. So basically your power would come as 3.5 into 10 to the power minus 6 watt, because we have not converted anything to dB here. Okay. Now, or if I convert that to 3.5 into 10 to the power minus 3 milliwatt, we can do that. Now I take the 10 log of it. So if I take the 10 log of this, it will come around. You just check whether it's a minus. Is it coming a minus? Just do the calculation just a little bit. 10 log of 3.5 into 10 to the power minus 3. Is it a minus coming? Just need to confirm. Is it coming? Minus? Minus coming, right? Okay. So this is the answer. So this is your reference power at D0. Now you have to find out, the question is, so this is the first part, find the received power in dBm at free space distance of 100 meters from antenna. Now the question is, what is the power at 10 kilometers? So which formula you are going to use? The one, that generic formula I gave you, the 10 log of something plus 20 log of D0 by D. So use that formula and get the answer. So I am referring to, yeah, same thing. So you are supposed to get something like this. 10 kilometers is given by I am writing in short PR 100. So this is your minus 24.5 plus 20 log of 100 by, we are converting 10 kilometers to meters. So this will be calculated as the overall effective resultant received power at 10 kilometers. Okay, so this will be coming around minus 64.5 if I'm not wrong with the calculation. So it's not about the final outcome, it's understanding the problem. So we are trying to measure at 10 kilometers, but in order to use free space model, we need a reference distance. In this case, the reference distance is 100 meters. So we are making the measurement with respect to 100 meters. We are taking that as a reference and then we are moving ahead in making the measurement. Now D can be anything, but the reference distance or the reference power is always minus 24 dB. Understood? That is what the calculation behind this is. That is a generic thing because L usually as an it's a loss factor. So ideally it is considered to be 1. It's like theoretically it can be proven. So even if L is not given to you anywhere, consider it to be 1 and carry on. And even for that matter, I would say that if suppose the gain of the antennas are not given to you, you can consider it to be unity gain and you can carry on. Okay, so these are the assumptions. Another thing, in many of these problems, you hear although it's mentioned, but sometimes the frequency won't be directly given to you. So please note down or remember, if nothing nowhere throughout this wireless, if nothing is given with respect to frequency, please consider F as 900 megahertz and compute. Because 900 megahertz is standard GSM frequency, so you can carry on with the calculation. So this is where we end the portion of for free space as a numerical. This isn't even. This is what this one. This value. Yeah, no. This is this one. This is nothing but D naught by D. You go back to earlier, just few slides back. This is the equation. This was the equation, right? This is what we are going to use. So this D naught is 100, B is 10 kilometers. So that's what I did. Same thing happened. Please remember this generic form also because in order to get the exact solution, you will need this. Suppose one of the problems you will get is, suppose instead of doing the last equation, for 100 kilometers you substitute the data in the first equation. Suppose you instead of in this equation you substitute 10 kilometers and you get the answer. You will get the answer, but theoretically that's wrong. You will get the answer, but since you have not considered the reference distance in our calculation, your answer will not be exactly correct. You will get an answer, but that's wrong. You will need to use the reference distance plus whatever the calculation is. Clear? Fine. So we'll end up our discussion on something very interesting, which is nothing but the derivation of the free space. Okay? So this is how we get the expression ideally. This is not exactly needed, but we have to introduce some terms. That's why I'm doing it. So this is relating power to electric field. This comes from some of the concept of one of your very favorite subject I came to know is EM theory. EMT, one of your very favorite subjects of yours, where you had very less amount of equations to remember, I guess. So you can see here, basically this is an isotropic radiation pattern. Now imagine a scenario of point source which is PT-GT, which is the EIRP we have defined previously. So PT-GT and it is radiating all throughout in equal direction, and you are looking at a small segment of it. Now if you are looking at the small segment, you can find out that what is the effective flux density or PRD. This is what we call as the flux density. Okay. So this is what we are trying to find out, and this is given by the amount of radiated power multiplied by the aperture of the antenna. Okay, so aperture of the antenna and all, if you substitute, you remember in the first case when we discussed on free space path loss, the first slide, I told you the gain of the antenna is related to the aperture of the antenna using an equation. So this is the equation. So this comes in from the aperture. This PD is nothing but the EIRP divided by 4 pi d square, because this is the total power radiated throughout the area. So a small segment. So you substitute overall and you get the answer for this. So this equation actually comes in because of the power flux density, which is power which is radiating out throughout a small segment of your isotropic radius. It comes from small segment. So that is what the idea is. But based on that, we come to a very important conclusion, which is the next slide. I want you to write that. So PRD, we now know that PRD, how to calculate what is the significance. But power can be related to E field using the equation E square by eta multiplied by AE. Please note down this equation. This is a relationship where the power or the radiated power or the received power can be related to the electric field in this case. Now, any idea about this? Eta? What is this? Eta? This is not path laws exponent. Same symbols being used, but this is not path laws exponent. Can anyone remember EMFT days, wave propagation? There was something called as when we did the propagation in wave propagation, there was free space propagation. There was dielectric through which it goes. We had something called as intrinsic impedance. No, sir. Don't remember at all. 120 pi is the intrinsic impedance of a free space. Okay? So please remember E square by 120 pi. You might ask, sir, why we are doing it? We are only doing it because we want to relate power with the electric field. Nothing more than that. It won't be necessary after this. It's just for this part we need. So P and E is related by E square by 4 pi because we are measuring everything with respect to free space. That's why we are doing it. A is the aperture of the antenna. I told you last time. So E square by 4 pi, right? So this is the equation and this relates the power to E field. Please make a note of it. Please make a note of it. E square by eta. This eta will always be 120 pi in terms of free space. It comes from the free space equation, like modeling actually. And finally, we conclude our discussion that PR can also be related to V square by 4R. This is the open circuit voltage. If you convert that to voltage, what is the RMS voltage being generated out of power? Because these things I think in fundamental electrical networks you have done, like relating power to E field, like electric field and all, or voltage to power. So PR can also be related to V square by 4R. So please note down this last equation. This is, yes, it is all related to antennas and it will also come from the electric field, the fundamental electrical circuits actually. So this is the relationship between power versus V with respect to free space modeling. Everything is with respect to free space. Okay. So you consider V square by 4R. Have you taken those equations? Right. Why I need it is because we will want to solve this equation. Please solve this problem. You can see this is a specific problem given in Rappaport that requires the last one. The magnitude of E field at the receive antenna and the RMS voltage applied at the receiver input. For this specific problem, we require those formulas. Otherwise, all throughout after this, you won't need it. So please try to solve using the given data. What is the answer for finding the receive power? Last slide will go. Just write this last expression. PRD is equal to V square by 4R. That's yes. Here we don't go for it. So you have assume a receiver is located 10 kilometers from 50 watt transmitter. The carrier frequency is given by this. Find the power of the receiver. Which formula you are going to use in this case? Which formula you are going to use for the first calculation, find the power? Do we have a reference distance given? We don't have. So naturally, since it's not given, so we will consider that 10 kilometers, whatever is given, that happens to be D naught. So you are going to use the PT, GT, G naught, lambda square formula and just substitute D. Instead of that, you substitute 10 kilometers. So whatever the value you get, that is your reference distance and that is your power. Understood? So since no reference distance is given, that is what you are going to get. So please compute it. Just a small drill, just 2 minutes it will take. GT is given as 1, GR is given as 2, so substitute that. Again, lambda will definitely come as 1 by 3, so that comes as 1 by 3 whole square. Power is in watt, so you can directly calculate in dB watt and then subtract that, add 30 to it, so you will get in dBm. You can find it in dB watt, or nothing has been mentioned, so you can find it in dB watt as well. Just substitute, what is the value you are getting?
Sir, it is
No, yeah, kind of, yeah. Only the GT-GR is different, so that will be a factor. GT-GR was 1 in that case. Guys, please do it. So you have 10, I am doing directly 10 log of 50 multiplied by 1 multiplied by 2 multiplied by 1 by 3 whole square divided by 4 pi whole square multiplied by 10,000 square. So if you take this and do the 10 log and all, you will get something as minus 91.5 dB watt. So this is your received power. If you want to, what will be in dBm? Plus 30. So you will get around minus 61.5 dBm. Okay. And for finding out the magnitude E, you have the formula square root PRD 120 pi divided by AE. Okay. And your V will be square root of PRD multiplied by 4R. R is given to you as 50 ohm. Okay. How will you get AE? How will you get AE? Do you have a formula for AE? Do you have a formula for GR? So we had a formula GR lambda square by 4 pi. It's nothing but GR is equal to 4 pi aperture by d square. 4 pi d square multiplied by AE. You go back to earlier slide. First slide when we did for free space. 4 pi AE whole divided by lambda square. So AE is unknown in this case. GR is known. So you substitute in that case and you get it. GR. Right. So this is all about the part. So we'll see how we can actually change the free space model into two-ray space model, two-ray reflection model, where we will take into assumption the non-line of sight combination. So that is what the idea is. So substitute these values and get the answers for respectively. I'll just give you the answer for this. Just try to calculate. For E, you will get the answer as I'll write it over here. 0.0039. I'm writing it in terms of volt per meter. And for this voltage, you will get 0.374 millivolt. These are the two answers. Please substitute and find out what is the answer. Okay? So we'll start with two-ray model. We'll finish off with the derivation next. Thanks.